This video introduces FPGA design using SystemVue's LTE library. This slide shows the concept of using SystemVue's algorithm reference designs to generate end-to-end test vectors as well as intermediate stage test vectors. These vectors can be exported from the SystemVue environment and into an FPGA development environment to verify the functionality of VHDL code written for an LTE FPGA application. Furthermore, the vectors can be used as part of a hardware test environment to facilitate hardware testing. This is the uplink transmit design in SystemVue, which has been designed to the 3GPP LTE specifications. So on the far left-hand side, we have a data bit source. To the raw data bits, we perform CRC encoding, adding the CRC bits. This is followed by code block segmenting, turbo encoding, rate matching, interleaving, and then finally scrambling. This reference design can be used to produce end-to-end test vectors for an FPGA or DSP development, or it can be used to generate intermediate test vectors at each stage of the coding chain. In our case, we're going to be taking a look at the scrambler block, and we're going to be using the SystemVue scrambler block to produce reference vectors to compare against HDL code that has been written for an FPGA implementation. So we'll pick off the input to the scrambler block, we'll run it into HDL co-simulation to co-simulate with this HDL code that's been written for an FPGA target. The output vectors from HDL co-sim or co-simulation are then compared to the scrambler output vectors using this element. And then from this, we'll calculate an output vector difference. So let's go ahead and perform our simulation. And this simulation has completed, actually the HDL co-simulation. And now let's view our results. So this column is the output vector from the SystemVue reference scrambler block. These are the output vectors from HDL co-simulation, and this is the output vector difference that is being computed with the element in that SystemVue schematic. And we can see that the output vectors agree, showing good correlation between the SystemVue scrambler and HDL co-sim. Now let's take a look at how the baseband exploration library can be used for algorithm development in SystemVue. So I'll go ahead and minimize this display. I'll make the schematic larger. And let's zoom in on the scrambler block. I'll double click on our C code scrambler block, and this model is polymorphic, meaning I can switch it from the C code representation to the math representation. You'll notice that when I do this, the symbol changes color, indicating that now we're using the math representation. Now this is hierarchical, so I'll open it up and I'll push down one more level. And at this level, we see the math representation for the scrambler block. Now I'll double click on it, and this exposes the mathematical algorithm that's being used to define the scrambler algorithm per the 3GPP LTE specification. So this serves as a starting point for you to customize the algorithm and modify the scrambler block per your interpretation of the LTE specification. I'll go ahead and close the subnetworks to go back up to the top level design. And let's go ahead and perform our simulation. So this time, we're using the mathematical representation of the scrambler algorithm to compare against the HDL code that has been written for the FPGA implementation. Our simulation has completed. Let's go ahead and bring up our table. And again, here we see the SystemVue scrambler output vector This time, this is using the mathematical representation of the algorithm. This is the VHDL co-simulation output vectors. And the output vector difference that's being computed shows good correlation between the VHDL co-simulation and the math algorithm simulation of the SystemVue scrambler. For additional information on using Agilent's LTE reference designs to generate vectors, please see the new white paper shown below. Thank you for your time today.